these kind of ideas. So, okay, with this, let's jump in. As you know, there are a lot of fermionic systems in nature. So there's high energy physics, and you have the constituents of the standard model, quarks and gluons in this picture here. And so these quarks are made of fermionic matter. So whenever you talk about either nuclear physics or lattice gauge theories, it's very natural to, have fermionic descriptions of nature. Similarly, there are systems like chemistry at lower energies and condensed matter physics where you have electrons interacting, and these strongly correlated systems, they're very difficult to be described in many physically relevant regimes. And, here there's this question, okay, can we do something else? And what's fundamentally different about fermions and bosons is this property that they have a exchange statistics, right? So the spin statistics theorem tells you that if you take two fermions, and here, sort of foreseeing our applications, I draw neutral atoms in a tweezer array. But basically, if you take these two fermions and you exchange them, you know that the many-body wave function of these particles is anti-symmetrized. So you will get this extra minus sign if you do that. And so that's a very fundamental property that on the one hand side needs to be taken into account whenever you do fermionic simulations of nature. On the other hand, this is also what you get in the lab by using fermionic particles as your constituents. So, well, let's dig into this a little bit deeper. And if you think about quantum simulation, as I said, you need to take into account this anti-symmetrization, and there are in principle two ways of doing it, or two different avenues. And I call one of them an algorithmic encoding. And so basically what you do is you say you may have quantum hardware based on bosons or based on qubits, and you want to simulate a fermionic model on these qubits. And if you want to do that, you have to take into account this anti-symmetrization, and there has been quite a body of literature that has been dealing with this. And by the way, all these reference lists, they're by no means complete lists, so I'm sorry if I'm forgetting something important here. But basically, for many of these fermionic problems, there exists efficient ways of mapping them into qubits. And this is what these papers have been dealing with. And if you think about experiments, then typical experiments nowadays targeting quantum simulations either focus on neutral atoms, trapped ions, or maybe superconducting qubits. And here we want to focus on neutral atoms because, as I said, neutral atoms, they come in these two different ways. They can either be bosonic or directly fermionics. And therefore, with neutral atoms, we think you have these unique possibilities of actually directly simulating fermions in the lab. And this brings me to this second side here, which one could call direct or hardware encoding. So there's a relatively long history now of a lot of experiments in a lot of experimental groups across the world where you use optical lattices, and using these optical lattices, you can trap atoms, both bosonic but also fermionic. And you can really create these systems really large and with high amounts of coherence and control in the lab, and directly study for instance, the phase diagrams or the real-time dynamics of fermions in the lab. And so if you want to do this, you can think, okay, can we use this actually, on the one hand side, these existing platforms that are already being used to study fermions in the lab, and combine them with novel technologies, for instance, optical tweezer arrays that have been developed since almost a decade now in order to study many-body physics. Can we use these? Can we combine this and create something that we might want to call a fermionic quantum processor? And so the fundamental idea behind this is, can we, use all these technologies that are currently being done to do atom-based quantum computation, but additionally have this ingredient that if we use fermionic atoms, this fermionic statistics is actually hardwired into sort of the workings of your quantum processor to begin with. And can we make use of this if you want to study these fermionic systems that we discussed? And okay, so I guess you've heard about these Rydberg atom arrays, but basically the idea is something like this. You initiate your system and you load these atoms into these optical tweezers. And now we think about something like a register that you could imagine like in this picture. So you have a series of these modes, and these modes, they can either be empty. You could think of it as a sort of information 0, or they're occupied as sort of an information 1. And then we can make use of these dynamic rearrangement capabilities of these atom arrays. So basically what that means is we can, for instance, exchange 2 of these modes. And this would be something like a swap on the logical modes. And if we want to exchange 2 of them, which are occupied, we additionally fundamentally get this minus sign out front here. So, okay, having said that, some of my colleagues have actually thought about how to, with this, design a blueprint for a fermionic quantum processor. So essentially they say, okay, let's have this register over here. What we need now is a specific set of gates in order to be able to decompose whatever operation I want to do into sort of parallelizable, individually locally constrained operations. So on the one hand side, there's something like a tunneling gate. So you might have one tweezer unoccupied and the other one occupied. The idea is you can bring them together. You can delocalize the fermion between these two using physical operations, and then you can separate them again and they will be entangled in a specific way. So there are different ways you could think about that. Well, first we can write down a unitary operation like this. And there are different ways you can think about that. For instance, you can actually physically merge the 2 tweezers and you tunnel them and then you separate the tweezers again. But you might also use different kind of tricks. You might use a set of storage tweezers and a transport tweezer. And then you can basically load the atom from a storage to a transport tweezer. You can move the transport tweezer around and therefore realize the tunneling interaction through this transport tweezer without actually having to tunnel. So the point being here is that it's different hardware realizations of doing that, but sort of the principle is always the same. You have to actually move the atom between the modes.
Question?
Yeah.
So it looks like at least what you are showing at the moment is spinless.
Yes. Yeah.
Is having spinful fermion state, I don't know, processor possibility?
It actually is a possibility. So what I'm saying here now is basically insensitive to this. So you can think of spin just as another mode. And you can, in principle, also put this mode wherever you want to. You can put it on top, and then maybe you can do something which is spin independent and therefore sort of parallelize between these 2 spin modes. But in principle, you can also spatially separate the spin modes, and then it would just be another location.
But
it's an extra freedom that you can
right. But if you want to actually think of it as like modeling physical spin, you would want those 2 states to actually be part of a SU2 symmetric space. Right?
That's right. Yeah. And
okay.
I think this is a good comment. And I guess it depends really on what you want to do. If you sort of fully digitalize everything, then you can keep track of that symmetry by hand, right? So you can put your spin down here and your spin up here, and you just need to make sure that whatever you do here, you also need to make it in the same way, such that this symmetry is preserved. Or if you want to use more sort of hardware properties of the processor, then you can try to actually make use of that maybe fundamentally some processes anyways SU2 conserving. So maybe you can save something on the digitization of this process by just sort of in a semi-analog way, do it in one go. But yeah, as I said, I think that this is just an extra knob that you can play with that can be helpful or not. Okay, so I think this tunneling is sort of one side of the coin, and this tunneling is actually, however, where you move the atoms and where this exchange symmetry fundamentally comes in. The other side of the coin are density interactions. So you see maybe you have two tweezers occupied, you bring them together. You can now use, for instance, the Rydberg interactions between these tweezers, like they do in the qubit atom arrays, and then you can separate again. So actually here, I can go back to some of the work that, for instance, has been done in Harvard and use these kind of hardware realization of these gates. And now if you have these kind of ingredients, you can combine this in different ways. For instance, you can decompose these density-dependent tunneling gates. So in such a way, you can realize a gate where sort of mode I can tunnel to mode K if and only if this mode J is occupied. And or similarly, here's another process that's very interesting, for instance, in quantum chemistry, where you have a pair tunneling process. So where mode K and L simultaneously tunnel to I and J. And it can be decomposed into these two mode gates. Okay, so there's one caveat actually, namely, since the atom number is conserved, and this will be a very important point further on, if the atom number in the experiment is conserved, then it also means that whatever fermionic model you simulate with will also have a conserved particle number, right? Because you cannot just create the atom, and if the atoms directly represent the fermions in your model, then this conservation law carries over. And usually this is fine, right? If you want to simulate quantum chemistry, you have a fixed number of electrons, so you would never want to have coherent superpositions between different numbers of electrons in a molecule. So then actually, if you can realize a local density phase here with this angle pi over 4, a tunneling operation with angle pi over 4, and here a control Z-like density interaction gate. So a phase that you imprint, a phase of -1 or minus pi that you imprint whenever two modes are occupied. If you have these three gates, then actually this is universal, and it tells you can decompose any many-body gate that you want to realize into these operations, and you have a universal fermionic quantum processor. Actually, if you take this one into account as a pair creation process, which here is not possible, you will be even beyond, it will be universal even beyond a fixed number state. Okay, so far so good. Now, however, if we take into account that, of course, these processes are noisy in reality, then we might want to implement quantum error correction for this. And as it turns out, if you want to implement quantum error correction, this number conserving processor is fundamentally an issue. So you actually do want to create superposition of different numbers because you want to be able to correct for instance, dephasing errors that might happen during your computation. So in the next few slides, I will try to first repeat a bit about quantum error correction and then explain to you sort of where this problem really arises. Okay, So in quantum error correction, the idea is you want to protect quantum states by encoding them into suitable subspaces of more particles. So maybe multiple particles, usually qubits, in this case, fermions and fermionic modes. But let me talk about qubits first. So here I discuss a repetition code. And so you can think of this little spin here being a plus, sort of a coherent superposition of up and down. And similarly, these will be minus states. So this will be up, minus, down. And you have two quantum amplitudes, alpha and beta, which contain the, if you wish, logical information about your state. So suppose you have a dephasing operation, and a dephasing in this case is a C operator. The C operator flips your plus to minus, and you do see that initially these phases, alpha, or these amplitudes, alpha and beta, they are unaffected by this process. However, you do change the structure of these code words, right? They don't point in the same direction, but instead the third one points in the opposite direction than the rest. So what you do is you define the set of syndromes. There's one operator x1 times x2 and an operator x2 times x3, while initially both of them were in their +1 eigenvalue. So this is a +1 eigenstate with respect to both of these operators. Once you have this dephasing operation, it actually turns out that the second order, the second operator would flip its eigenvalue to -1. So you do this measurement, you detect this -1 over here. You know it corresponds to the C3 that has happened, that was applied as an operator to represent your error. And you can correct for that by, again, applying a Z3. And the fundamental reason why this works is because this syndrome, x2, x3, it anti-commutes with the C operator over here. So if you want to go to the fermions, then we can actually think of a one-to-one correspondence here for a single mode between these qubit operators and actual fermion operators. And you see this C3 with eigenvalues plus and 1, it can be mapped to this occupation and this parity operator for the fermion. And similarly, this x2, x3, what it does is it changes the occupation state on mode 3 and mode 2. So we can identify it with this sort of 2 Majorana operator over here. And indeed, they anti-commute like you would expect. So it's fine. You can use this as a syndrome for parity errors for the fermions, or phase errors for the fermions. However, you see that this is not a number conserving operator. So this would fundamentally clash with your atom number conservation in the experiment, and you will have a hard time actually measuring this operator in practice. So the upshot is, if you want to protect against phase errors, you usually go into the opposite basis and try to make an equal weight superposition of the two. So you want to go to something like a plus state in this case, but you can't, because then the atom number is not conserved, and this fundamentally clashes. Okay, so one can, phrase this in different ways. You can also think of it in this way. And here I want to highlight a work by Alexander Schuckert and Michael Gollins, who are at UMD. And they worked out a very similar problem. Essentially, if you think of your error set as exactly this, you have phase errors in here, and you assume that you can implement logical states in a number sector. So assume your logical, whatever you call a logical one, would have a certain number of physical atoms inside maybe a well-defined spatial region that you might want to call a code block. And your logical zero is decomposed in or consists of a different number in zero many atoms. Then in order for this one to be a fermion and this one not to be a fermion, you would like n0 to be even and n1 to be odd, right? Because the total parity of this thing should be corresponding to sort of the fermion parity that you have in your model. And the total parity is the sum or the product of the parity of all your physical atoms. So if you now write down your error correction conditions and you actually plug in, for example, for this one, you pick the 1, here you pick a dephasing sort of C operator, and then you sum over all the modes, then you would find that your right-hand size is actually explicitly dependent on which ends you use. And it's explicitly dependent here on the index of the logical state that you're probing here. Yeah, so it's not true that this is fulfilled. So the C will be I dependent. And therefore you see it's a contradiction. So, okay, again, a different way of saying it, suppose, you actually have an operation which acts logically, but it also couples to the total number of atoms in there. It would actually realize something like a transversal logical operation in here. So also this is in contradiction with the Easton-Nil theorem that there's no continuous symmetry in a logical code block. So at the end of the day, all of this just hints to the fact that in order to realize logical states here, you inherently need number superposition in whatever logical units you use, and this is difficult. Okay, so what we did in this work is actually relatively simple. We said, okay, if we can't sort of inherently use this eigenstate of a fixed atom number to create logical units, then we have to realize these number superpositions, and therefore you need to take your system and you need to couple it to some ambient system, and you need to realize coherent exchange of particles between the two. So we define something that we call a fermionic reference over here. And so the kind of scenario that we have in mind is that you might have a processing unit in your system where you have optical tweezers. They can do fast rearrangement and exchange of modes. And you have a reference system. And as it turns out, this reference system needs to be very stable, and it needs to have kind of like storage capabilities. So we think of an optical lattice here, which sort of sits in the background and which has all of these atoms stored. And then what you can do is you can create sort of effective particles out of this. So effective particles, fermionic operator C here, that are consisting of physical particles S, and these physical particles S have the atom number constraint, and an operator R over here that we carefully design. It's a many-body operator, but it's carefully designed in order to transport a certain kinds of properties from the physical fermions to these effective fermions, such as the effective exchange statistics. And what we want this operator to do is we wanted to seemingly create a mode in this tweezer here, and we do it by taking a mode from this reference, taking an atom from this first reference mode and moving it to the tweezer. Yeah, so this whole state in an occupation basis, we would just define it by this label here that labels the occupations of the tweezer modes. And the idea is that we can define R as a unitary operator, and then if you take the anti-commutation relations of these system fermions, we can actually show that if you design it in the right way and on a suitable subspace, you would get effective anti-commutation relations between these modes C. Okay, and that's the task. We have to show that indeed, in the end, there are fermions. And well, you can look at an example. For instance, if I want to create two fermions in these tweezers, there's essentially two ways I can do it, right? I can first create the mode 2 and then the mode 3, or I can create fermion 3 and then fermion 2. So if you first create fermion 2, okay, we take it out here, we move it here, and then creating fermion 3 means we take the next fermion out of the reference and we put it into mode 3. So that is fine. If we do it the other way around, we actually realize that we first created here in this mode 3, but actually if I now want to move this fermion over here from the reference into mode 2, then I actually have to swap these two particles and I would get this minus sign over here. So you see for this simple example over here, indeed they're anti-commuting, so indeed they're fermions. Okay, and the defining property of this R is basically this operational task of taking the last occupied mode of the fermionic reference and annihilating the fermion there, and vice versa for our dagger. Okay, and that's basically sort of it with this construction. So by repeatedly applying these effective fermion operators, we can realize these superposition states, and that means, well, you can see here sort of the structure of the R tells you there's no actual structure in the reference other than how many atoms are left, right? So if you apply it to this vacuum state, first C2, and then you apply C3 dagger, then you would see actually these two are in a coherent superposition. And since the whole thing is kept in a coherent superposition, you can do this back and forth. So again, you can go back and so on and so forth. So you get the full Fock state structure on these effective fermions living in the tweezer.
Question.
Yeah.
Yeah. So it seems the way you're circumventing the conservation of atom number is by essentially dilating your system to have these auxiliary atoms that you can use to populate your fermion states. Now, practically speaking, how much do you have to worry about contamination when you're not applying these special population operators? Or like detrimental correlations between atoms in your reference that might affect the fermionic state, the logical fermionic state that you're trying to encode.
Yes, in principle, a lot. Yeah.
Okay.
So you can see it here, right? If there's some effect that these two atoms here do something that you don't want, you would actually decohere this part of the state with respect to that and the rest. Yeah, so in a sense, what we do is, I mean, I will show you how this can be used to do a quantum error correction, but basically what you do is you protect the tweezer part of your system sort of at the expense of the reference part of the system, in a sense that you really need to make sure that a reference is a stable concept, sort of a stable part of the system in your background that you can access, but otherwise is really stable and doesn't decohere on its own. Okay, I will get to a few other of these details in a minute, but actually, let me also, yeah.
I have a question for you as well, and I was wondering if you could step back for a moment, and I have some sort of mental picture for what you're using a typical quantum processor for, you factor numbers or something, and I can see how error correction works there and can help you.
Okay.
Now in this, it's not clear in my head what tasks you're going to use this fermionic thing for, and because I don't have that visual thing in my head, I'm not seeing what is the problem that's being fixed by doing the error correction. That makes sense to the question?
So, yes. Well, basically what we have in mind is quantum simulation of fermionic models.
Okay, so you want to do a quantum simulation of a fermionic model, and
yes.
you're taking sort of a digital perspective where you're going to apply a bunch of gates that do some trotterized evolution.
Yes.
Okay. And if I think in that perspective, there are various things that I'm fighting against. One is that you're just approximating the evolution with these trotterizations. Right,
Mhm.
this thing doesn't help you there, right? This is the other issue, which I think is what you're hoping this helps with, is those individual gates, you have limited ability to do them accurately.
Well, no, there's also the fermionization of the bosons. You have to attach strings to all of your operators to convert them to fermions.
Yes, yeah.
So he wins there big time. He
Okay,
doesn't have to fermionize because he already has fermions.
Exactly. Sort of the,
And I guess you can always do, I mean, so far the discussion has been, I guess the error correction is about like, if, assuming you know what state that you want to realize, you want to make sure you can actually realize that state. So then there's a question of how do you decide what state you want to realize, and perhaps the state that you want to realize might be ground state of some Hamiltonian, then this will be kind of a variational approach, VQE kind of thing. And unlike the qubit system, which can at best do spins, this will be, variational wave function of fermions. So that would be that will get around the trotterization problem. You can always try to do trotterization too, but.
I guess so I'm one. The Paul said something and it confused me, and you're doing it with fermions, right? Those particles there are fermions.
Yes, I
Yes.
think what Paul was referring to is that when people try to do quantum simulation of fermionic system, let's say chemistry.
Sure, but so the point is that, so you could just do trotterized evolution of fermions in one of these things, and you wouldn't need this extra bath. Right, so he's adding this extra bath for some extra.
No,
You have to do the error correction because you need to error correct your fermionic simulation.
Right, so that's the thing that is not obvious to me, is that you need to, what,
You want to calculate the energy of some molecule and it won't come out right if you're getting errors.
Your state is not what you think it is. So,
and so the, so I guess, the utility of error correction in this is just because I'm not familiar with thinking with this fermionic case. The utility of error correction is not obvious to me.
so I
Right, so
think-
But
yeah.
when you do the simulation, you're trying to calculate the energy of some nitrogen fixation molecule. If you do that in a bosonic system, you've also got to error correct.
So we shouldn't be comparing with both, right? We're doing, the question is comparing, you're doing some fermions versus you add on this extra error correction to it.
No, but you're always going to need error correction. I don't understand. Your question doesn't make sense. Why do you think you don't need error correction?
That you switch your physical X operator, use a logical X instead, you know that the logical is more well protected from noise, plus all the error correction output. Now, you can use bare fermion operator, you could run the simulation, but it's gonna be very, if you can come up with a logical version of the C-dagger.
Right, but you need, whatever the things you're going to protect from have to be already. They have to be more than the errors you're getting from, say, the trotterization.
Well, so first of all, like if you have a state, you don't necessarily have to trotterize. That's what I was trying to say. You don't have to necessarily be after spectroscopy or dynamics, right? So, I mean, his goal right now is that he has a way of realizing a fermionic state with fermionic degrees of freedom, and operating on it. But we all know that whatever scheme of realizing something is going to come with error. And there's an established framework for how you do the error correction with qubits, but because this fermionic,
So I'm
platform-
I'm simply raising the question of that established framework for
Yes.
doing error correction in qubits is that what you want to be using here for the fermions.
It
It is not.
doesn't work. He just
Yeah.
spent 4 slides telling us why it doesn't.
No, but these extra auxiliary things added.
Well, so this is a framework that they have developed
Yeah.
in order to do error correction for fermionic degrees of freedom, where number is strict, strict. quantum
We
number.
can discuss offline now.
Yeah.
Thank you very much, Robert. Sorry to.
Okay.
No, I'd like to ask just a quick
Yeah.
question. So I understood, what Shukert and Gollins did and showed that you can't create these operators and and be in a number eigenstate. What I'm curious about is all of this makes perfect sense to me theoretically. What you're probably going to get to, but as long as we had to pause, I'm wondering, has any of this been realized experimentally? I don't have any intuition at all for how easy it is to pull fermions in and, cause more problems than you're solving.
So it is definitely challenging. But there are platforms that are being developed into this direction. So naively speaking, I would say sort of all of the ingredients that I'm showing to you have been realized, but it hasn't been put together. But for instance, one experiment that has been recently done in the group of Adam Kaufman is they have a bosonic lattice, an optical lattice, and they take a tweezer ray, they load it with the atoms, they move it onto the lattice, they load it, and then they let it evolve in the lattice. So these kind of things are actively being pursued at the moment.
Okay, yeah, that was, thank you. It's not a complaint. I just wanted to know these things are really at the bleeding edge to be able to implement.
Yeah, but I mean, I won't claim it's not extremely challenging what I'm telling you here about. So yeah. And also, I mean, there are different ways of realizing this, and maybe, more generally speaking, also for qubit quantum computers, if you think about it. So the only way you can sensibly apply gates is if you have some notion of a phase reference in the background. So there's this question about optical coherence as well in qubit quantum computers, and there, we don't need to discuss this in so much detail because optical coherence sources, lasers, are just very, very good. So in a sense, what we're trying to build here is a coherence source for fermions, for fermionic number and fermionic parity, if you wish. And there's also different ways of doing that. For instance, what these people suggested in their paper is you can think of having something like dimerized or like molecule states here. So if you have a molecule, this is bosonic, and this bosonic molecule can condense, and you can keep it in the background, and then try to coherently build operators which exchange particles between the system and your processor. So in that sense, it's somewhat analog to a discussion about optical coherence in qubit quantum computers. Well, in sort of neutral atom qubit quantum computers. Okay, so suppose we buy this construction for the moment, then actually you can realize these states. And here I'm using this label, this occupation sort of label for the states that I was introducing earlier. And here for a simple repetition code, we could realize this logical 0 and this logical 1 over here. So you see it's an equal weight superpositions of all combination of having basis states that are even parity. And here you have all possibilities of having an odd parity state for that number of modes here. And again, I can show you these stabilizers over here. You can define logical operators, and you would see that this, defines a suitable code space for your problem. And so if you think about this now, the setup would be, you have these modes, they're occupied in some way in this coherent superposition, but you might have dephasing, right? So maybe these optical tweezers, they fluctuate in intensity or, position or whatever. And then what you do is you bring in the reference, you realize this controlled exchange, and with this do a measurement. And once you have this measurement, you know where the error has happened, and then you can very simply undo it with an actual phase gate that you can, for instance, do by shining an extra laser or adjust the tweezer or something. And so while I've shown you the construction of these states, we haven't really talked about this operation here. And so if you phrase this in a gate-based way, you can actually do it in the following. Suppose you here have your three physical modes. You have the reference in the background. And for instance, we could use extra qubits and use these qubits to, in the end, read out the syndromes. Then what you would do is you would first bring this qubit in an equal weight superposition of up and down. Conditioned on the up state, you might tunnel a fermion between the reference and one of these modes. You can also do it with the second one. And if you realize that kind of operation here with a specific angle, so this is a tunneling angle, I will show you in the next slide of pi/4, then you would write the eigenvalue of the stabilizer into the state of this ancilla qubit here. And a projective measurement over here would not tell you anything about the logical state in your three tweezer modes, but it would tell you something about whether or not an error has happened, and you can undo it in the usual way. So this was this element here. You have these syndromes, and you do error correction by applying this phase. So one thing is now, how do we realize this tunneling operation between the reference and this mode? And actually, the same operation in a qubit quantum computer would just be an X here. You would want to do a controlled sort of X rotation on your qubit with a certain angle. And this translates here to this operation, C dagger plus C, but we can plug in this operator over here. And indeed, there is a decomposition that you can find. One of the decomposition that you can find looks like this. And that's sort of one caveat. It is that actually to realize one round of error correction, you would sequentially have to go through the system. So this a process that in a qubit quantum computer you can do just in sort of finite, in a constant depth, so constant with the system size. And here it would actually scale linearly in the number of reference modes. And the reason is, I said earlier, this R is a many-body operator, and what it does is it annihilates the last fermion in this well, range of reference modes. It's occupied to a certain point, and the R operator should annihilate the last fermion that is occupied. So in a sense, this R operator, it's searching for the domain wall of this system. And in principle, you in order to do that, you have to ask sort of each of the modes where this domain wall is. So in principle, we decompose this into sort of this linear set of gates. And this red box over here would check whether there's a domain wall inside or not. So basically, you can decompose it as such. So this tunneling operation between the tweezer mode and this reference mode would happen in this case if, for instance, this mode is occupied, but the other one is not, then you know this is the domain wall, and you can do that.
Question?
Yeah.
So this reference state-based approach, is this specific to this essentially a repetition code? Am I right?
It's not specific to a repetition code. So what I'm showing on this slide here, we use for any kind of operation that changes the particle number inside of the processing unit.
Right. But is there a different kind of code other than the repetition code?
That's a very good question. So first of all, the construction that I've been showing, so I've been showing it for a repetition code because it's the easiest,
right.
But it can be generalized to any kind of even CSS code. So you can do, for instance, surface code constructions also similarly. There's two things, right? I've been only talking about Z errors. The reason is because detecting the Z errors is hard because you have to change the atom number. Actually, detecting, for instance, a loss of a fermion is much easier because you can just do it with N-type gates. For instance, with these density interaction gates, you can check whether sort of a bit flip has happened, for instance, through a loss of a fermion. So that's easier to check. And then in principle, in this case, you can just fill it up again if you found such a loss error. But therefore, I'm talking about the Z errors. But if you combine both of these things, you can go to essentially any CSS construction. Now there's a question, can you find other codes beyond this which have nice properties, sort of to be specified what they are, and additionally don't need to change particle numbers at all? And I think this is a more difficult question that's sort of ongoing research right now. So we're working on this. But sort of within this ordinary, stabilizer formalism, yeah, that's what you need to do, these number changing processes. And sort of the underlying reason is that, for qubit quantum computers, you want to have these well-defined code blocks that are essentially in a tensor space configuration. And here we have this global constraint. So we have a Fock space instead of tensor spaces, and that's sort of where all of this underlying comes from. So whenever you want to realize quantum error correction with this like simple tensor space structure, you would probably need something like this.
Question. So
Yeah.
the circuit that you need to use for implementing this R related gate or either I theta X is proportional to the total number of particles in the system. Is that right?
Yes, and therefore, yeah, exactly. It would scale linearly with the number of atoms in the system. We're thinking about different approaches. You might think that, I mean, here, as I said, this is like, an operation that sort of searches for the domain wall. So we're thinking like, okay, can you apply, I don't know, quantum search algorithms or something to do this more efficiently? Or can you maybe use measurement and feed forward or some of these approaches to do it more efficiently? So this is one construction that we wrote down, and it scales linearly. Again, exactly for that reason that I was mentioning, that it's not a tensor space. So this fermionic exchange statistics is sort of a global property of the system. And therefore, in order to realize these interactions here, you have this sequential thing that runs through something that scales with the system size.
So just this version of the implementation is actually having the same cost as literally implementing some kind of a Jordan-Williams string that would snake through the entire string.
Yes, that's true, but it's actually different. So we only need this operation if we want to do error correction. So your gates, suppose you can do your gates very well. So you can do many layers maybe of gates to run your simulation. And then maybe you do one layer of quantum error correction with a linear overhead. So I do agree it's not ideal, but it's apples and oranges at this stage.
Thank you.
Okay, so we looked at a very simple circuit. Okay, I should come towards the end. So for instance, you take 9 physical modes in the tweezers, and you build 3 logical modes in this repetition code. And suppose you initialize 2 logical modes in logical fermions, and you initialize a logical vacuum over here. Then actually what you can do is you can do these operations of exchanging them, right? And if you exchange them in this specific way, you move this, apply this operation to the wave function psi1, 2, you get it the other way around, and you should be able to see this exchange phase, this logical exchange phase in this case. So you can create a circuit like that. You can actually realize these gates. You can do errors, you can do correction. And indeed, if you simulate this, you see the usual property of a distance 3 code that you put in an error that in the uncorrected case decreases or sort of makes the contrast of your measurement go down with linear in this error strength p, and with this error correction you go down to p squared. And what we use for that is a set of logical gates, and I think there's much more that one can say about this construction of logical gates, and was not so much the focus of this paper, but essentially there's first of all this idea. So what we mean here is this logical swap gate, and indeed this logical swap gate, you can think of it as a transversal operation. So really implementing a logical swap is really just, taking these modes and classically exchanging them. Then there are gates such as T gates, and you might wonder how to implement them. And that's actually a nice property, since this T gate doesn't really have, it's not really about a fermion. There's no tunneling of modes, swaps or anything involved. So in principle, you could think of a qubit that has a T gate. So you can just take a qubit T state and in principle, inject it into your system in the usual way. Or you just realize this T gate on a qubit quantum computer and then basically swap it into your system like that. And the same thing, of course, you can do with density interaction gates. And one of the things that are a bit more tricky is this is supposed to realize a tunneling gate, but not sort of for the full angle, but something like a half angle, then it actually becomes a bit more complicated. But I think since there are now these new limitations of like this atom number, global atom number that you want to conserve, there's also sort of new opportunities or new boundary conditions on the gate design. So I think there are a lot of things that you can do differently as opposed to some of the standard ways that are being pursued right now. Okay, with this, let me come to the end. I told you about this reference construction and how it overcomes this constraint of having particle numbers. And there's actually this big question about, can you realize a fault-tolerant computation with this? And this goes back to some of the questions that you asked. Okay, what happens if this reference is being manipulated? If I have other spurious correlations in there, wouldn't this spoil my computation? Yes, in general it does. And the question is, okay, can we do something about it? And can we scale this to a fault-tolerant processing platform? There are also many different ways of realizing this reference. We talked about this linear in system size depth of realizing this. So we're working on alternative constructions there. Also different hardware realizations. I've showed you this other example of this molecule condensate state. And there's also this question, okay, on the algorithmic side, there are efficient ways of mapping fermions to qubits, but can we find examples where the fermions become really, really efficient against the qubits? Maybe not just quantum simulation, maybe there are other quantum algorithms where this extra minus sign can help. And more generally, I feel like there's a lot of quantum info applications that are sort of open to be explored. Many of these protocols that have been thought through for qubits that are different for fermions and also actually clash with this number constraint. One of these examples is teleportation, which you cannot easily implement on fermions if you have this constraint. So we're currently also looking into that. And yes, sorry for going over time. Thank you for the questions, and I'm happy to discuss more.
Question? Your two gates, can you go back to the, like, early on? You talked about your gate.
This one or?
No, the physical gate, like very early
yes.
on, yeah. So like with the qubit platforms, different platforms have, different varying degree of accuracy with their 1 qubit versus 2 qubit gates.
Yeah.
so here, your tunneling gates and your interaction gates. Is there a sense of, how the gate accuracy, fidelity would be different, similar between these two gates?
It's not super clear to me. So first of all, these gates, they're essentially Rydberg gates, or at least the way we think about them. So you can essentially use the numbers that current Rydberg atom arrays produce. So for these gates, it's actually more tricky. And I'm not sure if they in this way have been realized. I guess not. And some of the things that are a little bit tricky and different here is the following. If you have a tweezer, it's roughly in a harmonic oscillator, right? So if you're in the ground state, if you're really cool, you essentially occupy the harmonic oscillator ground state. But then if you move this around and you shake it a little bit, you would excite high emotional states of the system. So now, depending on how you initialize your gate, this can be a problem, right? Because if you have fermions, and for instance, if you realize a gate that explicitly makes use of the blockade of the Pauli exclusion, then of course that only works if they're in the exact same state. So if one of them is high up in emotional states, then this will be different as if they're in the same emotional state. So I'm saying there are different kind of limitations depending on how you use it.
These tunneling gates have not been implemented yet.
Not exactly in this way, but there are also, for instance, people in Munich doing gates, I think also in Zurich, doing gates with dynamical lattices. So also if you think about an optical lattice, and then if you put a second laser on top with like twice the wavelength or half the wavelength, you can actually, create these double well structures in an optical lattice and do something what they call an optical superlattice that you just get from the beating pattern of these two lasers. And actually, there's also a lot of things that you can do. And there you can also implement digital tunneling gates, sort of tunnel the atom from one lattice well to the other. And they have had very recent results from this year, which are reasonably high. Forgot the numbers, but something like 99.8 probability to sort of get the tunneling exactly right as you want it. But again, different mechanisms, and I think all of this is fairly recent.
Thank you.
Okay. Any more questions? If not, let's thank our speaker.
Thank you.
Thanks a lot. Appreciate the call.
Thanks. Okay, then I stop this. Okay then, thanks.
Thank you.
Thank you
Have
so
a
much.
nice day.
Appreciate it.